This lecture discusses the DRAM timing constraints and then how it affects application runtime or execution time. So in the last lecture, we discussed about the DRAM organization, the notion of ranks, banks, rows, and columns. In this lecture, we'll look at how accessing data from DRAM have different delays and how it can affect the performance. So just a background, if you remember, we talked about the notion of DRAM row, and row is also known as a page, different from the OS page. And we also have a row buffer, which kind of provides benefit if an application has spatial locality. And usually the DRAM will get a row and column pair for a given bank, once you identify the rank and bank. And there are three things that happen once the DRAM looks at a row and column. So if the row is closed, that means there is nothing in the row buffer. Then what we need to do is we have to send a command from the DRAM controller to the DRAM called activate. So this activate commands actually put a row into the row buffer. For example, row number X, if you are interested to get the data from, and that will be moved into the row buffer. Okay. Then comes the read or write command that you want to perform, depending on whether it's a load or it's a write back. And finally, there is a command called precharge, which actually puts the row back from the row buffer into the row X. Okay. So if this is the row buffer, the precharge will actually put the data back into the corresponding row X. Okay. So these are the three commands which will be scheduled by the DRAM controller. The DRAM controller will actually send these commands for a given rank, bank, and row and column. That go and activate a particular row, read or write from columns, and then finally put it back. Okay. If the row is open, that means it's already there in the row buffer. Then there is no need to go for an activate command, because the row buffer contains the data that you want to access. So you directly go and access that particular data, depending on whether you want to read or write. Okay. So let's look at the notion of row buffer hit, miss, and conflict, similar to our cache hit and miss. So this is a collection of rows and columns, and we have a row buffer that stores the recently accessed row, the last accessed row, and initially it's empty. Okay, there's nothing in the row buffer. Let's say we got a request of, let's say the rank and bank is fixed. We have already used our address mapping and we have extracted the rank and bank. And finally, we end up getting row 0 and column 0. So what will happen now is there is a row decoder which will decode and then go to that particular row. And let's say this is our row 0. Then we will actually bring it to the row buffer. So this is nothing but the activate command, right? Once we have that, we'll use a selector to select a particular column out of this row. Let's say, for example, this column. Okay, and then send it to the DRAM controller or to the upper level in cache hierarchy. So in this case, we are interested in the column address 0. So let's make it like this is column 0. Okay. So next we send the data back, and next let's say we get a request for column 1. Right, we get a hit because the row is already there in the row buffer. No need to do activate. Send it back. Similarly, now if we get a row 0, column 85, again it's a hit because it's present in the row buffer, the same row, right? So we get the column address 85, send the data back to the cache hierarchy. Now if we go for row 1, which is not there in the row buffer, then we'll actually get a conflict. And we are no longer getting a row for hit. So once we get a conflict here, what we need to do, we need to put the data back from the row buffer into the row 1. Okay, so that means what we need to do is we need to perform the recharge, which will put the data back into row number 0, and then we will go for activating the row number 1, right, through the row decoder. So now row 1 is in the row buffer. We'll use the column selector that will extract a particular column, and we'll send it to the upper level cache hierarchy, right? So if you look at the entire process in terms of delays and then the timing constraints that DRAM controller or the DRAM has to respect, there are 60 plus timing constraints that will be too much for this course. But few things that you should remember is that there is a latency that is associated for accessing a row, okay, and similarly for pre-charging, similarly to access a particular column. So, and the combination of these two is actually known as the row cycle time, right? You kind of access a row and then recharge it, right? That is the row cycle time. Once you get the row done, then you get the column, right? So the entire latency, whatever we are seeing here, is actually restricted to a particular bank, right? Remember, the address mapper would have already given you a rank bank, and these are the latency within a bank. But once you send the data will have its own delay at the channel, the bus through which the data will be responded back to the upper level in the cache hierarchy. So there are two policies that usually the DRAM system implements. So one is called the open page policy, right? It's about the row buffer, how you implement a row buffer once you get an access done, right? So in the open page policy, once the access is done, keep the page in the row buffer. As the animation example that you have seen, we are keeping the row in the same row buffer, assuming there will be future accesses to the same row, right? The best part of this policy is if the application has locality, then consecutive accesses will go to the same page and you will get row for hits. No need to get the data from the DRAM, no need to spend time in activating a row, right? But the moment you access a different page or a different row, you have to close the row, meaning you have to pre-charge the row, right? And open a new one. That means you have to activate a new one. The contrast policy is the closed page policy, where once you respond an access, if there are no accesses to the same row, then you actually close the page. So the key here is if there are no accesses. So usually what happens, so there will be a queue between your last level cache and the DRAM, and there will be a DRAM controller which will arbitrate and then it probes the requests which are coming, and if it sees that there are no requests which are going to the same row, then in the closed page policy, it will actually close the page, right? So which means if you access a different page, it will have better latency because there is no need to recharge, because you have already pre-charged after the access is over, right? So and this is good if your application doesn't have good amount of spatial locality. Let's say you are running a graph application, your code has pointer changing functions, right? So then this policy will do good, right? So modern processors, they actually implement DRAM controller, which is a hybrid of open page and closed page, and not a pretty simple policy that we are discussing here. So, okay, so at the top level view, if we want to summarize what we have discussed so far, if there is nothing in the row buffer, we have to activate on a given access, get the row into the row buffer, and then get the particular column. If there is something in the row buffer, there's no need to activate, only the column access latency. And if the row buffer contains something different, then first you have to pre-charge, put the data back, then activate, get the new row into the row buffer, and then access the column. Okay. So for this course, just keep it in mind that there's three variations that are possible, and the notion of pre-charge, activate, and column access. There is another important command that the DRAM controller uses regularly at an interval of 64 milliseconds for a DRAM that is running below normal temperature is the refresh command. Remember, DRAM is actually a volatile memory, and it's a capacitor-based memory, so that leaks data, right? So to make sure that the data remains and then the voltage level remains up to a threshold that is needed to keep the data in our DRAM cells, so we need to refresh it. So the notion of refresh is we keep on accessing the rows, all the rows essentially, so that whatever the DRAM contain at the particular moment of time, it should not lose, right? So this is a typical standard in some of the recent DRAM machines. You will find a different threshold depending on some of the internal subtle parameters, but more or less you can assume that you have to do refresh, let's say once in 64 milliseconds. Okay, and when you do refresh, you should understand that you can't respond to a load or store, right? So when you do refresh, your load is actually blocked. You can't do anything because the DRAM controller is actually sending requests to rows one by one for a given rank or a given bank, exploiting some notion of parallelism. But at the same time, you can't use the DRAM for servicing a normal demand load or a prefetch request per se. Okay. With that, let's move to the DRAM controller, which is actually an on-chip structure. It's not off-chip. The DIMM is actually off-chip, which will be placed in the DIMM slot. But the DRAM controller is actually on-chip, sitting just after the last level cache. And the DRAM controller actually converts the address that comes from last level cache into the rank, bank, row, and column. Okay. Once it converts them, depending on the request, whether it's a load, it will put into a queue called read queue. If it's a write back request, it will put into write queue. And then based on some notion of scheduling, it will actually start generating commands. So commands in the form of, let's say, activate, pre-charge, right? And it will actually try to improve our turnaround time so that the processor should not wait for long. And that's where the scheduling policy will come into picture. Okay. One thing that we should note here is the interface that connects the DRAM controller and the DIMM. So there is a command in address bus which is unidirectional, but the data bus is actually bidirectional, right? So in case of a load, you get the data from DRAM. In case of a write back, you put the data back into the DRAM, right? And these are DDR machines or DDR DRAMs, which means double data rate, which means you can actually send data in the both positive edge and in the negative edge, or the rising edge and the falling edge of the clock. So that's why if you look at the frequency of address bus, you will find that this is half of the data bus, right? Because address bus is actually getting accessed at a rising edge, we'll say. Okay. One more thing that you should keep in mind, there is something called a burst length, which defines in one go how much data can you send. And typically in the modern DDR DRAM, so you'll find that this burst length is actually of 8 bits, okay, and each bit is actually 64 bits, okay. So this is like, you can assume there are like 8 ticks, and in each tick you can send 64 bits or 8 byte. So you can correlate this with the example that we had in the last lecture when we are responding 8 bytes from different DRAM devices and then sending it to the LLC. So the DRAM controller actually prioritizes the reads because they are critical to the performance. The processor is waiting for the data, and it usually schedules writes when the write queue is almost full. So for example, if this is the write queue, let's say it has 64 entries, typically what the scheduler will do is it will see whether, let's say, 75% of the queue is almost full. Then it will actually change the direction of the data bus. Remember, data bus is bidirectional. So in case of load, it's actually going from DRAM to LLC. But in case of write, it's actually coming in the other direction, coming from LLC to the DRAM, right? So you need to change the direction of the bus, and once you change the direction of the bus, you kind of do a busty write, like whatever writes you had in the write queue, you try to get it done, plus out all the writes, okay? And during that process, the reads have to wait because the direction have changed now. So this can lead to additional latency. Okay, a pretty high-level view on the DRAM scheduling policy, where the goal of the scheduler is to send commands to the DRAM so that the turnaround time will be minimal. Okay, so you can come up with heuristics that tries to improve row for locality, or who sends the request, whether it's a prefetch request, whether it's demand request, right? And it does all this scheduling, satisfying all the DRAM constraints that we didn't discuss in this video. But there are like 60, 70 kind of timing constraints that DRAM scheduler has to obey and respect before sending a command to the DRAM. So a pretty vanilla level scheduling policy is FRFCFS, where FCFS stands for first come, first serve, right? But the variation of first come first serve is FRFCFS, which says first look for anything that is going to the same row which is there in the row buffer, right? So that's why it's called first ready. So you look at the read queue. So let's say this is the read queue, and there are commands like, okay, it's going to row 0, this is going to row 1, this is row 2, let's say this is row 0, this is again row 0, right? So the DRAM scheduler will actually go and search, and let's say this is the row buffer, and the row buffer contains R2, right? So instead of scheduling R0, which is in the forefront in the queue as per the temporal order, it will actually schedule R2, right? So that's called the first ready. And once you service them, after that, if you don't get any request which is mapping to the content of row buffer, then you can go for first come first serve. Okay. Another thing that you should be familiar with is the notion of memory clock and the rate at which the memory is transferred with various DDR standards, and how it can affect performance, right? So in today's world, you will find DDR5, and here 6400 stands for the transfer rate, which is actually in mega transfer per second. Okay, so if you multiply that with 8, you will get the bandwidth in bytes per second, right? So this is nothing but 6.4 giga transfer per second. You multiply by 8, and that will give you 51.2 GB per second, right? Another thing that you should look at is the transfer rate and the bus clock is actually the same, right? So the frequency at which the bus works is actually same as the transfer rate. Half as the transfer rate, not the same as the transfer rate, right? And so these are the things that you can look at next time when you look at a DIM, and try to correlate how it can affect performance, right? For example, if you look at DDR2, it provides only 1.6 GB per second, right? So if you consider a multi-core system, and let's say they are thrashing the cache, then 1.6 GB per second will be pretty bad. So the average memory access latency will be really high, right? The bandwidth will start affecting the latency. But with 51.2 GB per second, it may happen that all the cores are happily getting their data and at the same rate, and the average memory access latency is not getting affected. A few other things that you should keep in mind when we deal with shared resources like shared last level cache in a multi-core or a DRAM, which is shared by multiple cores, is that we can't just use the conventional metric like IPC, right? So IPC is good if you are dealing with only one core or one application in one core. But the moment you are dealing with a multi-core with shared resources, you should have a metric that should consider the fairness factor. Fairness meaning you should not improve performance of one particular core at the cost of another core, right? And if you just do IPC as a metric and then take a sum of all IPC from all the cores, right? Then finally you get a throughput. The throughput may show that, okay, your throughput is high, but it doesn't give a picture about what exactly happening to all the cores. It may happen that one core is improving by 4x and another core is going down by, let's say, half x, right? That means there is a 4 times improvement, there is a degradation in this case, but the throughput won't be able to tell you. Instead of that, what we should use is something called a weighted speed up, where what we do, we find out the IPC of a particular application. Let's say the application is I, running in core I. You run that application in a multi-core system, right? So you run app I in multi-core system, let's say an n-core system, and get the IPC, okay? And then you run the same app again in a multi-core system, but this time along with other core running application. Let's say this is IPC1, now you get IPC2, right? So usually when you run along with core running application, your IPC will go down because they will start interfering at shared resources, right? So IPC2 will be more or less less than equal to IPC1. So with this weighted speed up, what it is trying to see is whether your scheduler or your cache replacement or any idea that you are proposing for a multi-core, whether it's creating a big gap when you take the ratio of IPC together and IPC alone, right? And finally, it's adding all these ratios. So if it is considering fairness, then you should see that not a particular core is getting benefited, and at the same time, not a particular core is losing out in terms of performance. Okay. So with that, I will stop. Thank you.